Okay, I'm gonna get us rolling. It's 1 o'clock. People are rolling in. So I'll give a slow introduction for Diego. Hello, everyone. I'm Bill Hammond. I'm the AGU Geodesy Section Secretary. Thank you for attending today's early career AGU Geodesy Section online lecture. This is the first of the fall term. We're going to have another one in November on the 4th by Susanna Ebmeyer, who will talk about SAR, using SAR to study the dynamics of volcanism. But today we have Diego Melgar, who is a professor, associate professor at the University of Oregon, and a recent recipient of the John Warr Early Career Award. And the title of his talk today is The Future of High-Rate GNSS in Earthquake Observing Systems. So I'm gonna lock down chat, so please save your questions until the end. I'll probably unlock it about maybe 5 minutes before the end of Diego's talk, and we'll have questions for Diego at the end. So Diego, if you are ready, you can take it away.
Thanks, Bill. Can you see my full screen and not the presenter notes? Okay, I see a thumbs up from Luciana. Yeah, okay. Okay, well, thanks. Let me move the bar out of the, it's always in the worst place, this bar. Okay, thanks, Bill, for that introduction, and thanks, everybody, for taking time out of your day to come and listen to me. I'm going to talk about high-rate GNSS and earthquakes, and I'm going to cover some different topics, but I do want to acknowledge the funding agencies that have contributed to my work over the years, mostly NASA, NSF, and the USGS. And I also want to make sure that I acknowledge that I am not an island, and that the work that I've been able to accomplish has been in no small part by relying on the help of the people listed here and many others. I realized I'm very fortunate, and it took me a long time to list all the people that have contributed with code, ideas, time, writing, patience, and helped me to build up high-rate GNSS as a tool for looking at big earthquakes along my career, really. So thank you to all. And this is what I'm going to talk about today. And I thought I'd start here by posing a simple question, which is, for looking at big earthquakes, we have a perfectly fine, a more than fine, actually, worldwide seismic monitoring network. This is a map of the GSN, and as those of you who work in seismology know, there are many, many, many more stations than what are reflected on this map. And given that, why do we even bother with using high-rate GNSS for earthquake monitoring? It seems, perhaps at first blush, maybe unnecessary. So two things have happened that have led us to this. The first one is that we can do it. And like most things in humanity, sometimes that's good enough reason that we can, and so we do. The technology for high-rate positioning, and by that I mean a sample per second or faster with GNSS, has been developed over the last 25, 30 years or so, and is now very mature and very common. The second thing that has happened is that our response as a geophysical society to two big earthquakes, the magnitude 9 2004 Indonesia earthquake, well, magnitude 9.2, and the magnitude 9 or 9.1 Tohoku-oki Japan earthquake in 2011, our rapid response to those earthquakes, which relied mostly on traditional seismometers, was very underwhelming. So we kind of noticed that there was a gap there in our knowledge and our technology that needed to be filled. And that's where GNSS also comes in. So for that first point, as I said, it's been about 25 years or so, and I took a few snapshots here of some instrumental papers that have contributed to making the technology possible that enables 1 hertz, 1 sample per second or faster positioning. And you'll notice that I've highlighted 2 sentences here in these 2 abstracts from papers about 18 months apart. And they basically conclude the same thing, that high-rate positioning displacement stands to supplement, not replace, but to supplement essentially strong motion sensing, especially at the long periods. So that was 2001 and 2003. And then in 2004, the magnitude 9.2 Sumatra earthquake happened. And if you focus just here on the red symbols, those are the casualties in different countries around the Indian Ocean. 250,000 people died as a result of this earthquake, almost exclusively from the tsunami. And obviously the reasons why casualties were so high are complicated. There's a bunch of confounding variables that contribute to that. But one thing that happened and was an incontrovertible truth was that our response as seismic monitors of the world was very slow. At 15 minutes, the TWCs, the Tsunami Warning Centers, and the USGS NEIC, which is the de facto worldwide monitoring agency, had a low estimate of magnitude 8.1. Remember, this is a 9.2. An hour and a half that's upgraded to magnitude 8.9, which is still a lot lower. Remember the log scale of moment release. It's still a lot lower than 9.2. And the final magnitude was not known for days after that. So that's not ideal. And actually, Bill here, who introduced me, and others, realized at the time there was 15-second, I believe, I can't remember if it was 15 or 30-second sample GNSS, and noticed, hey, if we simply had looked at the displacements, it would have been easy to tell, based on where the stations were with respect to the earthquake, that something major had happened. And we should have been able to quickly say, this was not an 8.1, this was not an 8.9, this was something much larger. So I would argue that really this publication in 2006 is what sort of this, and there are others that appeared shortly thereafter, sort of kicked everybody into high gear to get serious about using GNSS as a monitoring tool, at least in rapid and real time. 2011 came around 7 years later, and it happened again. The magnitude 9 Tohoku-oki earthquake, here is this plot I've shown a billion times. The earthquake early warning system in Japan, the best in the world, reliant at the time almost exclusively on seismometers, or exclusively on seismometers, underestimated the magnitude as an 8.1 when it was really magnitude 9.0. We call this magnitude saturation. No surprises there. We know that that's a problem at magnitude 7.5-ish and higher, but it happened again, and it had the bad consequence that all the downstream products that rely on being able to identify earthquakes quickly struggled because of it. Tsunami warning at 3 minutes after the earthquake. This was the tsunami warning put out by the Japanese Meteorological Agency, JMA, who's in charge of this. And this is what the tsunami warning should have looked like. And this was sort of the post-event tsunami amplitudes. So clearly that underestimated magnitude led to an underestimated tsunami warning, not surprisingly. And 20,000 casualties from that earthquake, mostly from the tsunami. Again, a lot of confounding variables to why there were 20,000 casualties, an over-reliance on seawalls, and it's a complicated thing. I'm not saying that 20,000 people died because of magnitude saturation, but it surely did not help. And at the time, high-rate GNSS was in operation in Japan. This is GeoNet, the network operated by GSI, the Geospatial Information Authority of Japan. And this is an animation put by Ronnie Grappenthin shortly after the earthquake, showing, well, 500 kilometers of your coastline are moving 1 to 5 meters out to sea. You don't need to be a crack seismologist to figure out that this was not a 7.9 when that happens. So while this wasn't being used in real time at the time in Japan, it is probably the archetypal data set that we look at when we think about how to use GNSS for monitoring large events. So horizontals here on the left, verticals here on the right. So fast forward from 2011, another decade, and the following has happened, maybe a little surreptitiously, and it was a kind of quiet development, but a big deal nonetheless. In July of 2021, the date's right here, for the first time in USGS NEIC monitoring, the finite fault product, which you can see here in the event pages from the USGS, for the first time, that began to include regional data. For the longest time, the USGS has been making finite faults, and they've been exclusively reliant on teleseismic data. But starting with the Chignik earthquake, finite faults now include whatever regional data is available, That can be strong motion, like this sensor right here, but it also includes high rate GNSS and static GNSS. And as I'll show you towards the end, can also include INSAR. And so now when you see a finite fault product from the USGS NEIC, if GNSS, high rate GNSS was available at the time or in the hours to days following the earthquake, it should be a part of that finite fault. So it's been almost 30 years between high rate GNSS being talked about for the first time and it now actually being really in our monitoring systems today. So it's there. It's almost commonplace and it's expected to participate when we monitor earthquakes, but let's survey the roles, many roles that it plays, and I'll talk a little bit about where I think we ought to go as well. I order my thinking when I think about GNSS in this sort of timeline of response, where within seconds of an earthquake, a large earthquake occurring. Large earthquake means different things to different people, but let's say magnitude 6 or magnitude 7 and larger. Within seconds, we need to know how big the earthquake is and some rough estimates of where it is, maybe how long and how wide it is, something about the source parameters of the earthquake. And that's the role of earthquake early warning. And in this Cascadia simulation, you can see the little GNSS arrows unfolding out to sea, and that's the role that it plays there. If we learn something quickly about the source, we can then use that to inform hydrodynamic propagation models. So we can also leverage GNSS, and it's a super important tool for tsunami early warning or for real-time rapid forecasting of tsunamis. And that's within minutes. Remember, tsunamis can take 5 minutes, 10 minutes, 45 minutes to reach the nearest shores right next to an earthquake. Then when you get to the hours, that finite fault model that I showed you in the previous slide, that is a primary input into things like shake map that tell you how strong the shaking was. And Pager, which is a rapid loss estimation product that the USGS also puts out, and that's also informed by the finite faults. So GNSS at the scale of hours can also contribute, and not just with the finite faults, but also with direct estimations of shaking, even from GNSS velocities, as shown here in this nice paper from Brendan Crowell, which is currently in review. In the days after the earthquake, we find new stations or some data that hadn't telemetered quite properly comes back. So the models continue to be improved, and that continues to improve our rapid assessments of what happened. And that oftentimes is important, even in the days, a week, 10 days, 2 weeks after the earthquake, having an accurate story of what the earthquake was continues to be very important. And then you transition into the months where we start to see peer-reviewed studies, and I label this as a deeper understanding of just what the hell the earthquake was doing. And here too, it's become very commonplace, I would say almost a requirement, that any earthquake source model also include high-rate GNSS. In this nice paper by Dara Goldberg, you see the 2019 Ridgecrest sequence, which was a complex interplay of many cross-cutting faults, and teasing out the kinematics of all of these events relied on GNSS and strong motion and INSAR, but GNSS was also a fundamental player. And for all of these, and I'll talk a lot about earthquake early warning and a little bit about finite fault models and almost none at all about these two others, just because we don't have infinity time for you to listen to me drone on and on and on. But for all of these, I want to also highlight that the products themselves, which is what I'm going to focus on, they're only as good as the quality of the GNSS positions. And that's also a subject of vigorous research, which I'm not going to talk about too much here, but there's still a big need to improve the position estimates, especially in real time. Okay, so off we go. Let's start talking about the role that GNSS plays and will play in early warning systems today. I already told you that we know that seismic only systems begin to saturate at about magnitude 7.5, and we discussed that with the example from Japan, with the negative consequences to any product that depends on that rapid magnitude and location estimation. So what Brendan Crowell and others first noticed in 2013 was that in the GNSS recordings at high rate, there was potentially a simple feature that we could use rapidly to figure out magnitudes. And that's essentially the peak amplitude of any GNSS waveform, the peak ground displacement. Shown here in thick black are GNSS waveforms for 4 events going from 8.8, the Chile Maule earthquake, all the way down to 6.1, the Napa earthquake in California. And you can see the peak ground displacements are just that peak. And by comparison here, I show filtered and processed and integrated strong motion accelerograms integrated to displacement. And this is meant to show how at small magnitude, small PGDs, seismology and geodesy agree, but by the very nature of inertial sensors, as you get to bigger and bigger displacements, the inertial sensors cannot see those very big displacements for reasons I'm not going to get into. But this is a subject or a topic called baseline offsets in inertial seismology. So peak ground displacement, Brendan pointed out, was probably a metric we wanted to use if we were going to figure out large earthquakes quickly. And we took that and we ran with it. And by investigating all the events that had happened at the time, in 2015, we really only had 10-ish, 11-ish earthquakes that had been recorded by high-rate GNSS. We could produce a very simple scaling law where what you see here is hypocentral distance from the station to the earthquake, PGD on the y-axis, and you see that by magnitude, the earthquakes very cleanly separate. So the big separate from the not so big, which are separate from the smaller or medium-sized events. And with this exercise, you can produce a scaling law like this one right here at the top, which has PGD, distance to the earthquake, and magnitude. So if you know this scaling law before the earthquake happens, when the earthquake does occur, you figure out the distance quickly, you measure PGD from GNSS, and you can solve a simple least squares problem for magnitude in real time. And that's what we proposed to do, and which we show here in simulated real-time form for those events. The different colored symbols show the convergence to the final magnitude for those events. And the shaded regions in the background are the source time functions, which illustrate the moment release, or the energy release, if you want, of those earthquakes. And that's known a posteriori, many days, weeks, months after the event. And it works really well. There's no hint of magnitude saturation. All the solutions converge somewhere close to the final magnitude. I want you to note here for the Maule earthquake, for example, that convergence to the final magnitude occurs well before, half, a third of the way into the source time function. This is something we call weak determinism, that the fate of the earthquake can be known before the earthquake is finished. And it's an incredibly interesting subject that I'm not going to get into today very much. It's something that we continue to work on, but we've seen this repeatedly for other big events that have happened since. So, excuse me. That PGD magnitude algorithm has been deployed in real time into Shake Alert, the US earthquake early warning system. I believe it's not yet part of the full production system, but it's well on its way to being there. And in large part, that's thanks to the investment by the NSF, USGS, lots of state and local agencies into a very dense, high-rate geodetic network for California and the Pacific Northwest, which you can see here in these figures. And we routinely test MPGD, or it is routinely tested by big earthquakes in the US and around the globe, and it routinely works just fine. Here's an example from the Ridgecrest earthquake, where we see that PGD for the main shock, this is in 2019, converges somewhere close to the final magnitude of the event. Using the real-time solution. So on-the-fly computed solutions. This is a true real-time test. So that's great news because magnitude saturation is very bad. But we were still left to wonder, okay, but that's magnitude 7. And in the Pacific Northwest especially, we're very concerned with magnitude 8 pluses, magnitude 9s. So the question remained, will it work for the biggest of the big, given the network configuration in the Pacific Northwest and all of those things? So what we did to test that, because we haven't had big events, is to build kinematic simulations of large earthquakes. Here's a simulated magnitude 8.7. We simulated the shaking, which is these squares changing colors, that's PGA. And we simulated the high rate waveforms, shown here by the arrows quivering out to sea as the rupture pulse propagates through. And we saw just for this one simulation that the PGD magnitude converged to the right value, shown here in blue, while the seismic algorithm, this was a version of ELARMS, which is now deprecated, but it's not that much different from what's in operation right now. Stuck at around magnitude 7.6, saturated as expected. So this was a good confirmation that PGD would potentially work as a magnitude discriminator in the Pacific Northwest. So it works, we could say, except it doesn't always work. As with everything, there are always edge cases and things you didn't quite think about when you first thought about it. And so we expanded that testing. This is Amy Williamson's work. We expanded that testing to many, many, many more scenarios and created 1,300 scenarios of all sorts of magnitudes, like the ones shown here, for the Pacific Northwest. And we produced 1 Hertz waveforms at all of the stations in the Pacific Northwest, here colored by PGD. And here's some of the record sections for those 1 Hertz waveforms. Now, here's where things get a little iffy for PGD. I want you to focus on this model C. Model C has its hypocenter all the way off to one edge, and so the rupture propagates southwards. This is what in seismology you would call a unilateral rupture. The rupture is propagating solely in one direction. And when you use PGD with this kind of event, you get this black-gray line. PGD would almost estimate a magnitude 10, magnitude 9.9, when in reality the magnitude was 9.0. So we've made a mistake by 0.9 magnitude units, which is very, very bad. So we've solved magnitude saturation, but now we're worried about magnitude overestimation. And that's a kind of intolerable mistake for a system to make. Now, overall, PGD works really well. In this analysis of all these 1,300 ruptures, we found a pretty small magnitude error, plus or minus 0.18 magnitude units, which in real time is pretty good, but the occasional bad outlier. And there's no easy fix. There's no way to patch PGD quickly so that it stops making these errors with the unilateral ruptures. So we started to think we need something completely different. PGD is great as a stopgap against saturation, but we need something more advanced that can deal with these kinds of edge cases well. And that's where we got into using machine learning instead of the simple regression type approaches. So this is work by Junting Lin here at the University of Oregon, where what he did is he used those simulations to train a machine learning algorithm to discriminate earthquake source parameters. You can check out his code here on his GitHub page at junting/mlarge if you want to fool around with it or look at how he set up the RNN. And I'm not going to get too much into the weeds of how the machine learning algorithm works, except to say that because we don't have enough large earthquakes recorded by GNSS, we use the simulations as the training data. We add realistic noise to the simulations. And here is an example case for Chile. Here's a big magnitude. This is like a 9.2-ish, I forget. Yeah, okay, here it is, a 9.3 for Chile, simulated at the locations of the GNSS stations, generously furnished by CSN in Chile. And here are the waveforms for that event. And what we do is we randomly remove stations as well to simulate things like station outages and things like that. You want an algorithm that's resilient to that kind of thing, that real world situation where stations are sometimes not there because somebody shut up your radome, or the batteries died, or the solar charge controller got hit by lightning. And so what we did is we added realistic noise, removed random numbers of stations, and after making combinations of all these data augmentation processes, we end up with about 6 million training data points. We train with 80%, validate with 20, and what we're trying to do is predict the magnitude of the event as more and more GNSS data comes in. So this is a 5 seconds at a time update of magnitude. Then as a final test, we do have 5 real events recorded in Chile from magnitude 7.6 all the way to magnitude 8.8. So these events which have GNSS do not go into the training, and the algorithm is then asked at the end to also run on these real earthquakes. So here's the performance on the simulations that were left out. So this is on simulations. This is not on the real events. In earthquake early warning land, we've informally arrived, or at least I arrived at this sort of vision that as long as we're in the plus or minus 0.3 magnitude unit range, this shaded gray region, that's okay. We're doing okay for a rapid estimation of earthquake magnitude. Now you can see here that in the data set, you'll have to take my word for it, but there are many, many unilateral events in the training data. Events like that Model C, for which MPGD did not perform very well. There's many of those, and there's no inkling of this magnitude overestimation that we used to see with MPGD. So M-large, the machine learning approach, largely fixes that issue, which is good. Here is the performance on those 5 real earthquakes. This is a little blurry, I'm not quite sure why. But I want you to focus on the Maule earthquake, which is the biggest of them all. The red line is M-large's prediction or forecast for magnitude as a function of time. Down here in pink is the source time function that tells you the moment or the energy release of the earthquake. And once again, we can see that weak determinism in action where we can converge to a final magnitude well before the event is done. There's a slight overestimation and then that tapers down. It does pretty well for the other events with, little bumps here and there as the data is noisy and comes in. But overall, M-large does a much better job than just using the PGD magnitude estimation. But that's not enough. So what Junting has been working on over the last few months is the second version of this, which is not just to forecast the magnitude of the earthquake, but to also try to forecast the extent of the earthquake, or the source polygon, if you will. So shown here is the performance of the second version of M-large, where it's trying to estimate the source area, that's the blue region, compared to the pink region, which is the known source area from earthquake slip inversions. And the reason we want to do this is because if we know the source area, then we can also estimate shaking using something like a ground motion model. So here's the performance for estimating source areas for the simulations, and here's the performance for that Maule 8.8 earthquake. Now, if you're a little bit critical, you'll see a little bit these outliers, especially over the centroid depth, which is not too worrying, but the centroid longitude and latitude sometimes have these funky outliers. This is a little bit of an older animation. But I'll talk more about these outliers. These occur because of bad data, or not bad data, because of noisy stations or stations that are not really seeing the earthquake. They're just seeing noise because the displacements were too small. And we need a way to throw out noisy or bad stations. But anyway, that's not in here, and that's responsible for some of those outliers. But what's really cool is that once you know that source polygon, you can make this kind of magic happen, which is something I could stare at all day. The shading in the background is the estimated shaking. Now this is, for me, having started with GNSS now a long time ago as I become a grizzled old man, this is absolutely fantastic because what you're seeing here are estimates of shaking. So that's PGA going from 0 to 1G. That's some estimates of shaking you produced from crustal deformation information in real time. So this is what we want, because if you're a user of earthquake early warning, if you need to stop your train or take some protective action, which by the way, today was a great shakeout, how apropos that we're talking about it right now, to take that protective action, you need to know your shaking as a threshold. You need to know that your shaking is going to exceed the threshold at which you're supposed to take an action. So magnitude is a lot less useful than estimated shaking. So that we can do this is a great improvement. So what Tim's doing now, putting the finishing touches on a manuscript, is to assess whether this forecast actually compares favorably with the shaking that was actually felt or measured at specific locations. And by and large, we do pretty well, but stay tuned for that at AGU and in an upcoming publication. So HRGNSS in warning today is great, first because it finally puts to rest, even with just PGD, puts to rest the big bad wolf, which is magnitude saturation. And if we combine that with modern data science techniques like machine learning, it can be very flexible and provide you a lot more insights than just magnitude. However, GNSS still faces one challenging problem, which I think needs to be tackled or addressed for it to be a completely successful system. And it's that it is very noisy. Anybody who's ever looked at real-time GNSS data and sometimes even post-processed GNSS data knows all about the glitches, the cycle slips, the periods of reconvergence. There's all sorts of stuff in GNSS that oftentimes has nothing to do with the phenomena that you're interested in. And that's showcased here where I plotted the post-event solutions, produced using final orbits, final clocks, days or weeks after the earthquake, compared to the purple ones, which are what was actually streamed in real time and was available for use by systems. And it's much noisier, especially in the vertical. Although, the PGD is still not bad, so you still get to a pretty decent comparison between real-time and post-process PGDs. But it is true that GNSS and any seismologist that works with that exquisitely sensitive sensor that is the broadband seismometer will be horrified by the noise levels in GNSS. So there's a lot of room for improvement there. Here's another example of that. We looked at a year-long time series of real-time high-rate GNSS. This is the Central Washington University solutions. We archived for about 2 years, we archived about 200 stations, a subset of the west coast of the US, shown here in red, and produced stacked power spectra, PPSDs. These are called, you take hour-long chunks out of the time series, produce a power spectra, and you plot them all on top of each other, and you get this kind of heat map of where the noise is. And if you look at the year-long time series for bills, notice that the Y scale here is from -5 to 5 meters. That suggests many meters worth of noise in the real-time solutions, which is horrifying, not good, not useful for any kind of geophysical monitoring system. But when you begin to zoom in, what you start to see is that it's not that the noise is really that bad all the time, is that frequently there are these excursions away from the real noise of the sensor. So here's a week long, it's this red period here. You start to see that in between the noise spikes, the noise is actually much lower. Here's one period of reconvergence here. Here is an entire day, that's a zoom in of this. You start to see fewer and fewer spikes, and the values in the y-axis now are coming down. And when you look at it over a period of about 3 hours, which is here, you still see these two kind of glitches there, but you now begin to see that really the noise is centimeter level, which is what we need for real-time monitoring. And it's what's also revealed by the probabilistic power spectra, where you see that depending on the period you look at, you can even have sub-centimeter level noise in the displacements. But these glitches are there, and that's something you got to contend with. And ideally, we'd want to beat down the noise to have sub-centimeter, millimeter level positioning at all periods of seismological interest. So what to do? Well, machine learning is in vogue, so you just do that. And what we have started to build, this is Sydney Dibbing's work here at the UO. She's working on a convolutional neural network picker that is trained to discriminate between those periods of glitchy data and periods where there's actually an earthquake. And the idea is to put this in front of M large so that what M large receives is a waveform that we know for sure contains earthquake data, and we can throw out non-events and glitchy periods of the data. You might notice a theme here. We train on synthetic data because we don't have enough data from real GNSS. And for this particular project, we're testing it out on the 2019 Ridgecrest sequence. We've produced synthetic data at this network right here. It works pretty well. So this waveform shown here is a true positive. This is, now I'm hesitating, Sydney, whether this was in the synthetic or the real data, but whatever. This is a true positive event where the CNN is producing a prediction at red. It tells you where it thinks the P wave ought to be, and it produces a confidence level compared to what is really there. So this is actually really cool. The picker can work on sequential windows of data. And what it's saying is when it sees the earthquake, we've trained it to not tell you where it thinks the earthquake rises above the noise. It's actually telling you, based on the waveform, where it thinks the P wave ought to be if you could see it below the noise. So it tells you that, yes, this is an earthquake, and this is where I think the earthquake signal ought to start, the P wave. That's pretty cool because P waves are almost always smaller than high-rate GNSS noise levels. And here you can see some true negatives and a false positive and a false negative for the CNN picker. Just like any algorithm, it performs to a certain level. It's not magic. But what is interesting to see is if you start to pick apart when it works or doesn't work, you see the performance here based on magnitude and the peak ground displacement. But what I want you to focus on is this one here on the right-hand side, which shows that this is the log of the signal to noise ratio. So at signal to noise ratios of 1, which is pretty damn noisy, you're already getting to about 75% accuracy with the picker. And as you get to higher and higher SNRs, you get very, very high accuracy in the picker. So we're pretty confident that if we were able to put this in front of M large, it would throw away or it would not let through any of the glitchy bits of the data or any periods of just noise where there's simply not enough that has risen above the noise level of the GNSS sensor. The other thing you can do is instead of build a picker is you can denoise the waveforms. So use machine learning to remove the noise from the waveforms. We use the same training data set, the same workflow that we used for the picker, except we adapt a CNN designed by Zhu and Baroza for broadband seismic data and modified it for GNSS. This is Amanda Thomas's work. And we apply it to denoising the waveforms and try to see what its performance is like. And it's pretty great. Here shown an example is the blue is the signal with no noise, and its noise is in gray. So what goes into the CNN is the combination of those two. And as you can imagine, the way the CNN works is it uses the frequency domain information. So this mask is really kind of the spectra of the signal, and what the algorithm is trying to do is pick out the differences between the spectra of the noise and the spectra of the signal in order to remove it. So here is the target, and here's what the algorithm predicts, tries to remove it, and the outcome is over here in red. Red is the denoised signal compared to the blue, which is the pure signal with no noise. So in this case, it does really well, even in the verticals with really high noise. Sure, it has this little bit of drift, but compared to the level of noise, I'd say this is still pretty good performance for these synthetic tests. Here's a few more. On the left are synthetic denoised data. This is data that did not go into training, that is kept separate for validation. And the red, you want to look at the red and compare it to the purple, which is what you're trying to denoise. And you see that in pretty challenging circumstances, this is a signal to noise ratio of 1. It still manages to pull out a pretty meaningful signal, even if not perfectly, from the noisy inputs. Here is a real case where Amanda applied the denoiser to the Ridgecrest sequence to two stations, P570 and ISLK. And the dashed line is the real-time data, and the red and the purple are the denoised data. What I want you to notice from this is two things. Pre-event denoising is awesome. So removing the noise before the earthquake starts is the algorithm does extremely well. Look, all these noisy bits are gone. Denoising the middle of the waveform or the inside of the waveform does pretty well as well. But once you start to get into the codas, the denoiser has a bit of a hard time. So the denoised waveforms flatten out while there still seems to be some ringing in the waveform that is real. And we know that it's real because we compare it to integrated seismic data from a nearby station, Station WAR or Station ISA. So we know that that is really there. It's not noise from the GNSS. It's something we should be able to pick up. And the reason we don't pick it up, as I'll get to here towards the end, is because we don't have 3D propagation in the simulations. The simulations don't know about basins. They don't know about 3D geology. They don't know any of that. So all of those things that contribute to making waveforms ring for a long time, they're not in the simulations. And so the machine learning algorithm did not learn that behavior and cannot denoise it. So that's an obvious place where we need to improve. So this is what I think is the future of earthquake early warning. It's essentially apply machine learning to everything. And I don't say that as sort of a hipster fanboy. I say that because machine learning is a really easy way to solve really complicated optimization problems. Everything is an optimization problem if you think about it correctly. And so what you want to do is apply ML to these complicated optimization problems, maybe even at the positioning algorithm stage. This is something I haven't really talked about, but there's research that shows that that could be of benefit. If you leverage improving positioning algorithms with large real-time networks, add these algorithms like a picker or a denoiser in front of earthquake characterization algorithms, you can get to where you really want to be, which is the hazards forecast. What we want to know are the shaking and the tsunami. The earthquake source parameters are less important in real time. So actually, there's another class of algorithm we should think about where we forgo characterization of the earthquake and we jump straight from the data to the hazard without bothering to learn anything about the earthquake, at least not in real time. And that's what I want to show you here. This isn't my work. This is just something I'm very excited about. This is work by Don Sabrim and Randy Levesque. And what they've done is also pretty phenomenal. They took our simulations, here's 10 minutes worth of GNSS for a simulated Cascadia earthquake, and they trained an ML algorithm to predict the tide gauge recording from the tsunami that results from this earthquake. And so that's in blue. Blue is the ML prediction. Dark black, or the dashed black, is the hydrodynamic simulation of that tsunami. Now, this is absolutely amazing. This is at tide gauge 901 here, getting into Puget Sound. And the reason this is amazing is because the algorithm, the ML algorithm, looks at these 10 minutes or less worth of crustal deformation. And from that, it predicts a hydrodynamic time series without ever caring about magnitude, rake, strike, slip, length, nothing. It goes straight from the crustal deformation to the hazard itself, which is the time series of tsunami amplitudes. So that's something that I think we ought to do more of. And then the other thing that I already alluded to is that the Earth is 3D, so we should do a lot more work on that in GNSS and high-rate GNSS. This is work by Oluwaseun Fadugba here, a postdoc supervised by Valerie Sahakian. And what he's doing is he's applying SW4, which is a really advanced supercomputing code for waveform propagation. And he's testing it out in Japan, where we have a really good 3D model. And he's using real events that have occurred and been recorded by GeoNet. And he's already showing with initial results, look at this gigantic difference between red, the 3D propagation, and green, the one-dimensional radially symmetric propagation. There's just so much more richness of detail in the red, and it's beginning to look a lot more like the black, which is the real recording. Now, for machine learning, this is really challenging because these supercomputing runs take a while. So thinking about doing 50,000 of these is not something we can do now, but there's techniques we can bring to bear, maybe from machine learning as well, to synthesize waveforms from three-dimensional geologic models. So that's something that needs a lot of work as well. So here's my timeline of events. I've spent a long time telling you here about earthquake early warning and maybe drawn some allusions to tsunami early warning, though I did not spend a long time here. There's a lot more to talk about. Just here in the final 2 or 3 slides, I do want to highlight the advances in finite fault models and how these can be used for a deeper understanding of earthquake source processes. Here, GNSS plays a fundamental role. I've already talked about the USGS NEIC finite fault data product, which now is beginning to include regional data like high-rate GNSS. Now, the reason that's important is because the finite faults can actually change, sometimes drastically, once you move from including just the teleseismic data, which is shown here on the left. Here's 3 events, 8.2, 7.2, and 6.0. Finite faults with just teleseismic data. And once you include the regional data, whether that's INSAR, GNSS, accelerometers, or a combination of them, you start to see very different patterns, not just in the slip, but in the temporal evolution of how that slip occurred. So there are many open questions in large earthquake dynamics, such as this one of the weak determinism business, that could be perhaps tackled by having systematically processed finite faults of all large events over the last 30-ish years or so. Having that database would be a huge boon to observational seismology that could be brought to bear to tackle these problems. The USGS database of earthquakes currently has 240-ish magnitude 7 plus finite faults, but of these 240, only the ones since the Chignik earthquake have regional data. That's, I don't know, probably 5-ish, 6-ish. So what's missing is to go back and reprocess these older events to go hunting for the GNSS, the strong motion, and the old INSAR, and introduce it into the old events going back to 1990. So we should be adding the INSAR from the Landers earthquake, for example, into these models. And if you're interested in slip inversions, this code used by the USGS was first developed in Chile at the CSN by Pablo and Sebastian and others They developed it for their own real-time products, and then this was adopted by the USGS, and it was expanded to include GNSS and INSAR. It's publicly available. Look for the slip inversion user on GitHub, and you can look for the WASP code. I have to admit that we've been a little bit lazy, maybe, in our documentation, and that's something we're working on, and we're trying to put together some Jupyter notebooks as well so that people can get up and running quickly with the code. But I think it's in a good enough state that if you were to download it and look through it, you could maybe do some damage. But it's on our minds to do better with documentation and with training people on how to use the code. So here's my timeline of GNSS. I hope I've convinced you that GNSS has a very important role to play at timescales that range from seconds to minutes to hours to days and even months. And of course, way past that into years and decades. That's the métier of tectonic geodesy, which is probably how geodesy first came to be in the limelight. But when you shrink that timeline down to the seconds, there too, GNSS has a lot to contribute, which is the reason why GNSS is the best geophysical sensor ever, period. Thank you. And I guess, Bill, I'm not sure how we're going to deal with the questions. If you want to read some questions from the chat, or if I'll let you negotiate that with our audience. Thank you.
Okay. Yeah, thank you so much, Diego. That very stimulating talk. There are a few in the chat, so I'm going to maybe go through some of those. I'm going to ask anyone else if they want to ask a question verbally. They can do so by raising their hand, and I can call on you. And I'm going to allow you to unmute yourselves for that purpose. Just one second. Okay, but let's start with the chat. This one's from Hugo. Diego, thanks for your wonderful talk. Do you use fault roughness in your simulations? If not, are you planning to consider it?
We do not, but we can. So for those of you that are familiar with kinematic rupture modeling, like this or like this, we've basically rewritten the Graves and Petrarca method, which is very famous, of synthesizing, of creating ruptures and synthesizing waveforms. We've rewritten it and modified whatever we needed to for GNSS. GNSS uses chunkier, fatter subfaults. We don't need small subfaults like you do in broadband, in strong motion broadband modeling. So we do not include roughness. I am aware of Rob Graves's work with including fault roughness by simply offsetting the faults from each other. So we could implement that. There's nothing stopping us from doing it. But for GNSS, without having done it, I doubt that it would have a very big effect in the synthesized waveforms. But again, that's saying it without having it done it. So maybe we ought to.
Okay, let's do one from Annie Kazanav. Thanks very much for the nice presentation. I'm not an earthquake expert, but do you need a minimum GNSS station density to provide magnitude estimates? You showed examples in California and Chile. What about the Mediterranean?
The minimum is 1. And if that station is really close to the earthquake, it can still kind of work. In the Maule case, which is this magnitude 8.8 shown here, even though there's many stations now in the modern Chilean CSN network, at the time, only the yellow ones existed. So for this entire polygon, which is the 8.8 earthquake, really only 2 stations were really close to the earthquake. And even then, we can produce a pretty good solution. So if the station is really close and it has really nice clean data that shows a big rise above the noise, 1 or 2 or 3 can be good enough. We have done some bits of testing in the Mediterranean from time to time. The Aegean Sea earthquake from 2014 is in the PGD database. We've looked at other events like the Lefkada earthquake and a few others. We've worked a lot with Athanasios Ganas at the National Observatory of Athens, and it's worked out fine. So sort of in retrospective simulated real-time processing, PGD has worked out fine, and there's some open source reports out about that. But we have not collaborated with them further in terms of implementing anything in real time.
Okay, there's more from the chat for you, Diego. From M. Alcazar. Kautsar from Indonesia. Great presentation, Diego. How about adaptive filtering, removing GNSS multipath models to denoise the signal?
Yeah, so we haven't looked at that, and I'm not familiar with how quickly that could be done or implemented in real time. So it's possible that non-machine learning solutions are just fine and have as much to contribute as the machine learning solutions. Anything that beats down the noise is good, and I'll take it. Whether that be from machine learning or from some other source, and anything that allows you to discriminate that glitchy boxcar signal or that period of reconvergence from a real earthquake is totally fine. I'm not aware of any of these being implemented in real time, at least not here in the US. In the US, by the real-time data providers that are going into Shake Alert. But yeah, it's something that is worthwhile exploring.
Okay, they keep coming. From Claudio Quinteros Cartaya, is it possible to analyze MW less than 6 using high rate GNSS?
As long as it's, so I guess this is as long as it's above the noise. And, we have looked at a few small events from time to time. The limiting factor is always the noise level in GNSS. So if maybe I can annotate, or I think maybe we disabled annotate. Oh no. Can you see my annotations here, Bill?
Yes, a little green line.
Yeah, the green line. So right around here is the usual level of GNSS noise. And if you look at these lines, which are lines of magnitude, for a magnitude 5, even at 10 kilometers distance, you're still below the noise of traditional high rate GNSS. Even at magnitude 6, you need to be pretty close, 10, 20, 30, 40, 50-ish. You need to be at 50 kilometers in order to see a magnitude 6-ish. So that's really the limiting factor, and why we're so keen on sort of millimeter level high rate positioning, so that we can see smaller events and more subtle signals as well. So magnitude 5s are possible if your station, right now they're possible if your station is right on top of the earthquake. Otherwise, it's going to be really hard. I feel like maybe even the Mogul earthquake, Bill, that you guys had out in Reno, I feel like there's one station that saw the Mogul earthquake, but I feel like Christine showed that to me one time. Anyway, yeah, so that's the limiting factor, the noise in the GNSS.
Okay, from Fabrizio Romano at INGV. Great talk, Diego. Do you think GNSS can also help to constrain magnitude and fault area in case of tsunami earthquakes? Thanks again for your work.
I do. And I do. And I should have talked more about that. And I didn't highlight Tara Nye's work. She's also working with Valerie Sahakian here.
Are you frozen, Diego?
Am I? Can you still hear me?
You're frozen.
No.
Oh.
Am I frozen? Am I unfrozen now?
Yeah.
So Fabrizio, yeah, I do think you can see it because, I don't think, no, actually, I do have that plot. Always come prepared with extra slides. Valerie made this amazing figure that I absolutely love. Here it is. So here's a tsunami earthquake, the Mentawai earthquake, a 7.7 in 2010. And here are GNSS waveforms for normal, regular megathrust events, these 4. Shown here in blue, green, yellow, purple, and red. The Mentawai waveform from GNSS, look at this extremely long ramp up to final PGD. It takes about 50 seconds to go from 0 to its final PGD, while the time from 0 to final PGD is much faster in the traditional megathrust earthquakes. So what we're working on now is how to build this into the simulations, so that when we train the machine learning algorithm, it's capable of distinguishing, because of this long ramp up, that this is a tsunami earthquake or a shallow rupture. I'm not a big fan of the tsunami earthquake nomenclature, a very shallow rupture. So I think it's totally possible. So that myth that GNSS has no resolution offshore is that, it's a myth. Or rather, it's only true for static GNSS. Time-dependent GNSS has all sorts of features like this long run-up that will allow you to have resolution offshore. So yeah, I think that it can totally help with that as well.
Cool. Okay. From Jeff Kennedy, great talk. Thank you. Do you think real-time gravimeters as ultra-low frequency seismometers could provide displacement data with lower noise than GNSS?
I don't think I'm qualified to answer that question, knowing absolutely nothing about cryogravimeters and real-time gravimeters. I am aware of the work done in France and Japan and elsewhere showing the instantaneous gravity signals from large events. So I think there's value to those data. You're still limited by the physics of rupture. So even if we had gravity data, which circumvents P-wave travel times, there's still the issue of whether there's enough information in the first few seconds of a rupture to tell you that the earthquake's going to be big. But without knowing how much they cost, how they're deployed, how they're built, or anything about gravimeters, of course I think they have value. Though while I think that GNSS is an awesome geophysical sensor, I'm an omnivore. I'll consume whatever geophysical data is proven to be useful.
Okay. Diego, you're doing great. Your stamina is Glenn Mattioli asks, what about Doppler for low magnitude events?
I have no idea, Glenn. Yeah.
Okay.
I have no idea. Yeah. Stumped.
Okay. So this one asks, did you use simulated rupture direction in machine learning? Does the impact of not using rupture directivity in the forecasting make a difference in the forecasting?
It's in there. So here's an example. Sometimes we have bilateral ruptures like this one. You can see the rupture pulse moving out. So the way the simulations are made is we make the slip pattern following the Graves and Petarka method, which I know means nothing to a lot of people, but we make the slip pattern. And then from a single slip pattern, we make the hypocenter be in a random location. So sometimes we have bilateral ruptures like this one. Sometimes we have unilateral ruptures like this one that I showed early on. Like this one. This is an early run before we added 3D geometry. But this is a unilateral rupture where it starts at one side and moves to the other. So directivity is in there. And that's the reason why this is much better than just PGD magnitude, because it's capable of dealing with unilateral ruptures or bilateral ruptures.
Okay. A couple more. Luciana Estes asks, says, enjoyed your talk, Diego. Thank you. I have so many questions. So here I go. Let's do her first one. I'm curious to learn if a unidimensional ruptures from the south to north, you also observed increased magnitudes. If not, could the overshooting of the magnitude in your C example was due to the stations that you were considering? I might be.
Yeah, I think that's about this. Yeah, the ones that misbehave, like the Malinka earthquake in particular, it's at the far edge of the network over here. That's the Malinka earthquake. And really, there's only one station that sees it clearly, and the other stations are kind of far away. I actually don't have that slide, and I thought about adding it. But Tim has a wonderful movie where he shows that most of the scatter comes from bad data. Basically that station was too noisy, or that we had no stations close to the earthquake when he did that random dropping out of stations. And so most of the misbehavior comes from that. So it's still not magic. It's garbage in, garbage out. So if we have bad data going in.
To clarify, I was referring to the Cascadia example.
Okay.
Not Chile.
Oh, the Model C. I see.
Yeah.
I see. Yeah. Wait, hang on. I'm catching up. So this has to do almost completely, in the PGD case, it has to do almost completely with the unilateral nature of it. Because of the regression method that is used by MPGD assumes a point source. So when you calculate the distance, it's from the station to the hypocenter. So what ends up happening is, if you imagine stations over here where there's a huge slip patch, these stations think they're very far away from the earthquake because we're using hypocentral distance, but they end up having really large PGDs because they're close to a large asperity. So the algorithm says, oh, I moved 5 meters and I'm 800 kilometers away from the earthquake. It must be something ginormous. So it really is the point source, the simplifying assumption of the point source that causes all the headaches here.
Okay, so even if you had put like the stations in Alaska, you wouldn't be fixing this problem.
So
You
if you
know,
had,
like to
if you had,
increase your aperture in a way.
yeah. If you had stations that you comfortably use to say these stations are not seeing the event, so you could, then in earthquake early warning, I've seen the term used, data not arrived. So if you could have stations that you could comfortably say these are non-earthquake stations and they're a certain distance, you could maybe use that. The problem with GNSS is still the noise. You're still at 2-3 centimeter noise levels, so you never know if you didn't see the earthquake because the signal wasn't big enough or because your station was noisy. So yeah, I don't know, that would be hard. And also, it would take a long time for the earthquake to get there, right? If you increase the aperture, and that would slow everything down. Yeah.
Okay, I shut down the chat to make sure that we could finish on time. But there is one last question.
Sure.
And that is, what is the ideal GNSS data processing method for this type of analysis? PPPAR or GNSS?
PPPAR, or what was the last one? Oh, differential.
Probably
Like,
differential.
yeah. Anything that arrives promptly with low noise. In the early days when I was a graduate student, we were doing network positioning, and that worked fine as long as you keep the motion of the base station out of the solutions, which makes it tricky, right? You need to know when the earthquake hits the reference station so that you can keep that out of the solutions. But if you had a way of doing that with confidence, then that data would be just fine. So my answer is low noise, low latency. Whatever fulfills that is the best source of data.
Okay. Diego, thank you so much. Really appreciate you taking the time to speak with us. So that's going to conclude today's lecture from the AGU Geodesy section. Please join us on November 4th if you'd like to see a lecture by the other recipient of the John Warr Early Career Award. All right, thanks everyone.